Well, what if we have some lone pairs? The ones we've looked at so far, there were no lone pairs on the central atom. Lone pairs just make things more interesting. So we can talk about the electron geometry, which is the arrangement of the electron groups. Or we can talk about the molecular geometry, which is the arrangement of the atoms. Okay? If you have no lone pairs, they will be the same. Exactly the same. If there are lone pairs on the central atom, then the electron geometry and the molecular geometry will be a little different. So let's look at ammonia. Let's throw up the Lewis structure real quick. Yeah. So there's the Lewis structure. And when we look at this Lewis structure, we ask ourselves, how many electron groups? 4. 3 single bonds and a lone pair. A lone pair is a group. Single bond is a group. There's 4 groups. 4 groups make a tetrahedron. So here is the tetrahedron with the 4 groups. 3 of them end with an atom, and this is a lone pair. So how I like to think of it is that I make this structure with the balloons, but lone pair balloons are invisible. They're clear. You just see right through them. So this is invisible. The molecular geometry, we're just going to look at where the atoms are. That lone pair of electrons, we can't see it. If we could see atoms, we still couldn't see the lone pair, right? This is so tiny. So we're just looking at the atoms. So we make that invisible. And just make it invisible. And this is the shape we get. So with the model, so here's a tetrahedron, but this one has a lone pair. So I take one of the atoms off, and that empty bond there is the lone pair. So the arrangement of the electron groups is a tetrahedral shape, right? But the arrangement of the atoms is not a tetrahedron. It's called a trigonal pyramid. So I'll bring that guy back. So this is called a trigonal pyramid because this nitrogen is not flat, it's not down in the same plane with the hydrogens, it's sticking up a little bit. It's a very short pyramid, right? And the base of it is a triangle. So that's a trigonal pyramid. Yep. The molecular geometry is only looking at the atoms. The electron geometry is looking at the electron groups. Yeah, it's the geometry of the atoms. The electrons, though, affect the geometry of the atoms, right? So we can't look at this and say, well, there's 3 atoms, it's trigonal planar, because it isn't.
So the arrangement of the atoms.
Yeah, you look at the arrangement of the electron groups first, and then you just sort of mentally erase. It's not that you're popping the balloons, because then the others would move. They're still there, they're just invisible, right? They're pushing the others away, you just can't see them. The weird thing about lone pairs is they're actually more repulsive than bonding pairs. Like, yeah, but wouldn't that be smaller than having an atom here? Well, the thing is, when you have a bonding pair, here's a nucleus and here's a nucleus, that bonding pair of electrons is kind of contained between those 2 atoms. Whereas here's a nucleus with a lone pair. The lone pair goes off and it can expand out, and it's not necessarily this teardrop sort of shape. That's how we like to draw them because it's more like the balloons, right? But that expands more, and so it pushes those bonding pairs together a little bit. So we just kind of have to remember that. So here's the ideal tetrahedral geometry where we have 109.5 degree angles. Because there's a lone pair here, the atoms get pushed together. You don't have to remember 107, but just less than 109.5. The lone pair is going to squeeze the rest of them. He's repulsive. Gross. Nobody wants to sit next to him. Let's look at water. Lewis structure for water. Well, we've got oxygen in the middle. Oops. Oxygen. And a hydrogen over here. This is how we generally draw it. How many electron groups on the oxygen? 4. What do 4 groups do? Tetrahedron. So the electron geometry is tetrahedral. There's 4 groups, they're going to make a tetrahedron, and then 2 of those are lone pairs, so they are invisible when we try to do the molecular geometry. So here's what I'm imagining. Well, actually, let's use this one because this is the balloons. I'm looking at the balloons, and well, 2 of the balloons, actually, I want to keep that one. 2 of the balloons are invisible. I'm going to make that one invisible, and I'm going to make that one invisible. And then I've got this shape. And that's called bent. All those other fancy words, right? In here, this one's bent. So throwing you a bone, here's an easy one, bent. Now, I erase these 2 because then I can look at this in the plane of the screen and see it more clearly. They're looking at these 2, and you can still see that that's bent. And these are the 2 lone pairs that would be invisible. Why is it bent? So there are 4 electron groups. And those electron groups repel each other. And so they're like pushing away. We don't like each other. We want to get as far away as possible because that's lowest energy. Okay? So you're okay with there's 4 electron groups there? So 2 of the electron groups are lone pairs. So when we talk about the molecular geometry, we want to look at the molecule, the big part of the molecule, the atoms, right? So these 2 lone pairs cause these other 2 bonds to be closer to 109.5 degrees. They're not 180 degrees, right? And so then we look at the balls in the ball and stick model and we say that's bent. Okay? You still have questions? Go ahead and ask it.
Okay, so we just call it. No, I get it. It's not linear. We're just calling it something different because the lone pairs are factor.
Yeah, the lone pairs make these go in a different way. The carbon dioxide had 2 groups, and the 2 groups got away from each other, but there's nothing else in there interfering with them. Right. So you just get away. But this one, we've got, I don't know why I did that.
Why are they necessarily repulsive?
Well, it's the electron groups are repulsive to each other. So these are, they're pairs of electrons, they have negative charges, and so negative charges don't like to be next to each other.
Right. But as far as the atoms?
Well, the atoms are along for the ride.
Right. They're just being pushed wherever.
They're just being pushed wherever, yeah. It's the electrons around the central atom that are repulsing each other. And these, for our purposes, have no effect. The atoms don't matter at all. Okay? Is that better? So we have to talk about the 2 geometries because the electron geometry determines the molecular geometry. But the molecular geometry is what we're interested in. So let me restore this. So this would be an ideal tetrahedron, but the actual geometry here, This isn't an angle of 109.5, it's 104.5. So it's squished even a little closer than in ammonia, because now we have two lone pairs, and they're extra repulsive, and so they squish the other guys a little bit closer together. And again, I don't expect you to remember 104.5. You should know that it's less than 109.5. So for relative repulsion of electron groups, lone pair to lone pair is the biggest conflict, the most repulsion. A lone pair and a bonding pair is medium, and a bonding pair with another bonding pair is the minimum repulsion between groups. So the number of the lone pairs affects the bond angles. And we need to be aware of this, but again, I don't need you to memorize this. So here we have methane. We have 4 electron groups, no lone pairs. So they're going to spread out equally 109.5. In ammonia, we have 1 lone pair that's up here, and it's going to push the bonding pairs together a little bit, because the bonding pairs are not as repelled by each other as the lone pair and the bonding pair. So this angle is less than 109.5. And then in water, we have 2 lone pairs. And so we got 2 lone pairs. They are repelling each other a lot, and then they're also repelling these bonds. And these 2 bonds are thinking, well, relative to that going on, you're not so bad. I'm just going to squish a little closer to you so I can get a little further away from him. Right?
Is this like the negative energy is less? Oh, so the ones that are being shared, like it's not so much.
Yeah, the negative energy here you could think of as being sort of contained, right? When we looked at this picture, so you can think of this negative energy as being sort of contained, and here it's not. It's tied down here, but the rest of it is going wild, if that helps you remember. Yeah, we have to try to make sense of it. And sometimes making sense of these things, these are very abstract things. I mean, this is one of the less abstract concepts in chemistry, and yet it is still abstract. I can't show you the actual thing, right? And so we have to come up with something in our mind that helps us remember. And that could be different for everybody in the class. I like to have pictures. I think of kind of stories. I make the atoms and the bonds and stuff be like people, because when I can relate them to how people behave, then I can remember, right? So if I showed you these 3 molecules with the information about their lone pairs, I wouldn't expect you to know that this is 107 and this is 104.5. But I would expect you to be able to tell me that this angle is smaller than that one. Okay? Just smaller. And this one is smaller than that one because of the lone pairs.
The 2 lone pairs, that's the biggest effect of repulsion?
Yeah, these 2 lone pairs, there's 2 big angry lone pairs over there are causing these guys to get a little closer together.
So the more lone pairs we have, the greater the effect will be?
Yeah, the more lone pairs here, the smaller the bond angle between the remaining, the actual bonds. Yep. Okay, so what's the molecular geometry of a molecule whose central atom has 3 bonding groups and 1 lone pair? So first ask yourself, well, how many groups total? 4. 3 bonds and a lone pair. 4 groups, so then what does 4 groups do? Tetrahedron, right? And 1 lone pair means that 1 point is invisible. So then we describe the shape of what's left. Trigonal pyramid. And like I said, you don't have to be able to pronounce it, and I won't laugh at you if you say it wrong. Trigonal pyramid, it's fine. They're kind of mouthfuls, right? What's different between planar and pyramid? That's an excellent question. planar means it's in a plane. It's flat, right? And the pyramid sticks up, like the Egyptian pyramids, they come up to a point in the middle. Any other questions? Well, what about 5 electron groups with lone pairs? We have to go through all the possibilities here. Well, let's look at SF4, Lewis structure. So we start out like this, nice, 4, we can get 4 around here, this is great. And then we've got 6 valence electrons for the sulfur and 4 times 7. See, that's 28, 34. So I'm going to count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I have 2 more electrons. Where can I put them? On the sulfur. Sulfur is in period 3. It can expand its octet. It can be an exception to the octet rule. And so I'm going to squeeze those in. They are on the sulfur. They're not just floating around. They are on the sulfur. So then when I look at sulfur here and count electron groups, I have the 4 bonds, 1, 2, 3, 4, and the lone pair. That's 5 groups. And then I think, well, what happened with the balloons when we tied 5 balloons together? Well, that was the little ballerina girl with the skimpy tutu, right? So here we have, well, that one's X'd out, right? So here we have the little girl, and here's her tutu. So the electron geometry is trigonal bipyramid. This makes a triangle, and that goes up to a pyramid on that side and a pyramid on this side. Bipyramid is 2 triangular prisms. Pyramids, I mean. 2 triangular pyramids. But now we have to decide where are we going to put the lone pair, because all the angles here are not the same. The angles between the axial and the equatorial are 90 degrees, and the angles between the equatorial positions are 120 degrees. We want to put the lone pair where it's going to have the most space. And so that's going to be in the equatorial position because it has more space. We're not going to see this in the axial position because here it's going to have 90-degree interactions with 3 other groups. Here it has 90-degree interactions with these 2 groups, but 120 with the others. That's more space. Okay? So then, for the shape of this, we mentally erase that, and we get this shape. And it's called a seesaw, which, why do I call it that? So here is my trigonal pyramid, and the lone pair is going to be in the equatorial position. And here's my seesaw. Oops. So, gotta look. This is fun. Playing with toys. Over here. Teeter, totter, bread and water. Okay, fine. They don't want to look. Anyway, that's the seesaw, right? Yeah. So they're showing it to you drawn like this, but it's a seesaw. Any questions about that one? What are the angles? That's good. Well, the angle here ideally would be 90, but with that lone pair, it's probably going to be a little less. And the angle between these 2 ideally would be 120, but it's going to be a little bit less. They're going to be squished together a little bit. BRF3 has 2 lone pairs. So here we have 5 electron groups and 2 lone pairs. So we see the 5 groups, we think trigonal bipyramid, and then here's 1 lone pair and the other lone pair. And again, the lone pairs are going to come in along the 2-2. And I guess maybe you could think of this as, you can't take the little girl's head off, or her feet, but you can take part of her tutu. Does that make sense to help you remember? No? You don't like that? I don't know. These things, that one I'm just making it up as I'm going along. That's what I do with all of them. It's just some of them I made up a couple years ago. So those are where the lone pairs go. And so then what we have left is this shape. And again, we're not trying to make things difficult. That's called T-shaped. Here's my teeter-totter. My seesaw. So if I remove another one, then I've got a T shape, right? Just shaped like a T. Now they draw it on its side, but tip your head, it's a T. And again, the bond angles there would be slightly reduced, but the book tends not to mention it for these bigger ones. Xenon difluoride. So here's the Lewis structure. We have 1, 2, 3, 4, 5 groups. 5 groups, trigonal bipyramid. So here's our trigonal bipyramid, and then we're putting the lone pairs along the equatorial positions because that's where they have more space. So now the little girl has an invisible tutu. Okay? So then the name of that, ignore the gray sticks, is linear. Oh, interesting. We could have linear with 2 groups. We can also have linear with 5 groups and 3 lone pairs. So the key to be able to remember this is to first master, okay, what do 5 electron groups do? What do 6, 4, and that helps with think about the balloons. What do the balloons do? And then you got that shape in your mind, and then you start erasing things, making them invisible for the lone pairs. This is the trickiest one because you have to remember, well, which position does the lone pair take? Because they're not all the same. In the tetrahedron, they're all the same, so it doesn't matter where you put it. But here, they're not. 6 electron groups. So here, BRF5. Here's the Lewis structure, and we count 5 bonds and a lone pair. That's 6 groups. 6 groups make an octahedral shape. In the octahedron, all of the positions are equivalent, so it doesn't matter which one we call the lone pair. You just take one of these off, and this is what I've got. So this is a pyramid. It comes up to a point, but the base is a square instead of a triangle. Square pyramid, right? So our octahedral shape, this is our lone pair, and then when we look at just where the atoms are, this is our square pyramid. Because here's the base is a square, and then this is the pyramid coming up. Okay. Well, what if you have 2 lone pairs? So xenon tetrafluoride is an example of this. This is where, if we just look at the formula, we can really get ourselves into trouble predicting shapes. Xenon tetrafluoride, oh, there's 4 groups, it's tetrahedral. But no, it's not, because there are 2 lone pairs on the central atom. So there are 6 groups. It makes an octahedral shape. So we took this one for the lone pair, and then it does matter where the other lone pair goes. So the other lone pair repulsions are greater than lone pair bonding pair repulsions. So the lone pair wants to get as far away as possible from the other lone pair. And so that's going to be on the opposite side. So we take that one off on the opposite side, and now we have something that's planar, it's flat, and it's a square. Square planar. Easy to draw. Now, here's an interesting question. what would those bond angles be? If these atoms are all the same, and they are, it should be 90 degrees. Exactly. Because the lone pair up here is pushing those away, but the lone pair down here is pushing them back equally. And so they're not bending up or down, and they're just going to be perfect 90 degrees. This is probably too small for you to read from where you're sitting, but this is table 11.1 from your textbook, which summarizes all the stuff we've talked about this morning. And I'm not going to give you this table on the next exam. It looks rather overwhelming, all that information. But if you go back and review the lecture video and think about how I explained it, if you just think about the balloons and then making invisible balloons and what's the shape, it is all actually pretty straightforward. You just have to get to the point where you can see it, and you're all capable of doing that, right? I mean, the math here really is just counting to 6, right? And if you don't remember the bond angles, you'll probably miss like 2 points on the next exam, so not a big deal. Lone pair repulsions. So imagine that a molecule with 6 electron groups is confined to 2 dimensions. So this one's flat because we said so. Therefore, it has a hexagonal planar geometry. So it's flat in the plane of the screen. If 2 of the 6 groups are lone pairs, where would they be located? So the choices we have are positions 1 and 2, 1 and 3, or 1 and 4. So 1, and where's the other one going to go? As far away as possible, right? So the other one would be down here.
And we just picked those because they're the furthest away from each other.
Yeah.
Right? We're not dealing with the three-dimensional.
This is not three-dimensional.
Yeah.
It's flat, right? It's just to see, do we have the idea?
Right.
Can we extend this to something else? Then we know we understood.
Do they do that when they're, so say we're back at 5.
Mm-hmm.
Well, 5 groups, right?
Mm-hmm.
And they take the equatorial position.
Mm-hmm.
Do they do the same thing as far as getting away from each other, or do they just?
Well, that's an excellent question. So let's go back and look at that one.
That's
So
what we were just on. Okay, yeah, they were like kind of close to each other.
yeah, so here there's 3 positions here in the middle.
It doesn't matter. They're the same.
It doesn't matter. Yeah. So this is as far away from each other as they can get, right? So, yeah.
So on our conceptual question, we were able to put it at 1 and 4, but in a 3D model, we can't put them figuratively at 1 and 4 because the head.
Yeah, well, it depends on how we count. So if we make this 1, 2, 3, 4, 5, just kind of randomly. Are you asking why isn't it 1 and 3?
Yeah, because like our conceptual question, we were able to put it at like what we call the head and the foot of the dancer, but
Right.
look at it 3D, we can't put them there.
Yeah. So that question gets a little complicated. So why isn't it here? Because they're farthest apart from each other. Well, we also have this whole 120-degree angle thing in here, and the 90-degree angles with the bonding pairs is better than the 90-degree angles with the lone pairs. And so it's not at all obvious, but this is better. So just kind of go with, we're making parts of her tutu invisible. Yeah. I mean, we could go into that, but I don't think you'd enjoy it. But it's an excellent question and a very, very reasonable
Well,
question.
it's just like, I didn't really like the answer on our conceptual question because we've already learned that you can't put them there, so when I look at the conceptual question, I'm like, well, we can't put them there, so that should be the answer.
Right. So what's a little confusing about this is we can see that, in 3 dimensions,
Yeah.
right? And we think we've been doing all of this 3-dimensional stuff on a 2-dimensional screen, and so we're like, oh, well, that's, the 2s and the 3s are the 2, right? And so why isn't it this way? But this one's flat. Actually, though, if this was 3-dimensional, because this is 8, an octahedral, 6 instead of 5, they would go here. And you'd get a square planar. Yeah. So, summarizing VSEPR theory, the geometry of the molecule is determined by the number of electron groups on the central atom. The number of electron groups is determined from the Lewis structure. Each of the following counts as one electron group: a lone pair, a single bond. A double bond is one group. A triple bond is one group. A single electron that might be found in a free radical is one group. The geometry of the groups is determined by the repulsions. Bond angles can be different because multiple bonds are bulkier than single bonds, and lone pairs are more repulsive. So the bond angles can get a little wonky. But that's your summary of VSEPR theory. So which statement is always true according to VSEPR theory? Always. That's always a dangerous thing, right? The shape of a molecule is determined only by repulsions among bonding electron groups. That sounds good. The shape of a molecule is determined only by repulsions among non-bonding electron groups. No, that one's definitely wrong. The shape of a molecule is determined by the polarity of its bonds. We haven't even talked about that yet, so that's probably not the answer. The shape of a molecule is determined by repulsions among all electron groups on the central atom. Yeah, that sounds right. Because it's the lone pairs, the non-bonding pairs, and the bonding pairs. Right? Does that make sense?